Welcome to the 1982 Nobel Prize in Physics. This one went to one person and one person only, Kenneth Wilson. He won for his theory for the critical phenomena in connection with phase transitions, which sounds like a lot of weird sciencey stuff, right? Who cares but a bunch of guys in the lab? Well, you do, actually. You really do care. So when you deal with different phases of matter, you're talking about things like a solid, liquid, gas. Those are all different phases. Plasma is a different phase of matter. We needed a functional understanding of the critical points of these phase transitions, but we needed it over a large scale. It's not like, oh, this works for, certain things in this temperature range. This works for the difference between a solid and a liquid. This works for a liquid to a gas. We wanted one theory that kind of covered everything and covered it well, instead of just inside certain ranges. Because up until his work, you had solutions, but they'd occasionally mathematically run off to infinity or negative infinity or go someplace crazy. And it just, you want a predictive number so that you can understand what's going on in these phase transitions. Well, why? Well, first off, the work was done back in 1971. In 1971, we were doing a lot of new engineering. We had jet engines, we had other things that were really coming online. I mean, they had jets in the 60s. We're talking much bigger, much faster, much different jet engines than they had before. Computers were changing. Lots of the technological stuff in the world was changing, and we wanted to get a handle on what material was going to be best for what function. Now, it does more than that. Remember, this is such an important topic that it's not just work done in 1971 that won the prize in 1982. There were two other Nobel laureates around this particular prize area in 1962 and 1968, but they only worked in very specific ranges and not over this broad spectrum of stuff. So this is a much more general theory than the previous Nobel laureates. Now, why do you care? Why do we care about why something's a liquid, solid, or gas? I mean, why does it make a difference? Well, let's dig a little deeper. So the work primarily allowed it was vital because we really wanted to understand that behavior in different conditions. And the applications were pretty far ranging. So if you want to know the material properties of something, you have to know those phase transitions, because let's say you're building a jet that flies very high. So you go from hot temperatures to cold temperatures. You're building ocean vessels. You want them to last a long time, building spacecraft. All these things make a big difference. And the material properties under those different conditions can be quite extreme. Engineering applications, thermal management systems inside your computer, inside a car, all these things, it really does matter. Climate science, we want to know when things undergo a phase transition so you can predict different pressure zones around, and get a little bit better version of a little bit more accurate version of the nightly weather of what's going to go on tomorrow. And if you think about it across the last 20 years, especially, that's come a long way. It even gave us advances that helped LCDs and LEDs and things that go into our flat screen TVs. So without this understanding of these phase transitions inside pretty much every material across all phases, we lose out on a lot of really nifty technology. So yeah, it may sound like a bunch of stuff in a lab for geeky people like me, but it does much more than that. It really does affect your life. And the more of this fundamental sciencey stuff we can figure out, the better off we can produce these technologies. And not only can we produce them, but we can produce them cheaper because we don't need to do as much testing. We don't need to do as much. Let's go off and build 900 of them and test them. We can build far fewer of them and test them. And it's going to work much better because now we have a theory to say which one should we really try. And those things we build are going to be much safer. And what that does is it passes it on to consumers and it becomes much cheaper for these things. So think about flat screen TVs when they first came out, prices through the roof, right? Well, now they've come down quite a lot over time. And I know technology always gets cheaper, but technology gets cheaper because we understand it better and we understand the science behind it. And that is things like the phase transitions. It really does matter. It's not just stuff for people in the lab to go, "Ooh, look, we figured out why it goes from solid to a liquid." Well, yeah, we did. And that matters to when you go off and try to build things. So this stuff is important and it does affect our lives, and it makes the products we want to buy better and less expensive. So I do hope everybody's enjoyed. We'll see you on the next Nobel Prize. I'm enjoying doing these videos. Soon we're going to get into a new series on the channel. This kind of started a little bit already, but I'm going to get much more active in that particular series of talking about things that are going on in the modern world. And I think we're going to dive into things like gravity waves, certainly James Webb is going to be on the topic list, and more importantly, what do we understand about gravity? What don't we understand about gravity? And why are scientists continuing to work in that space when it seems pretty straightforward? Hey, it's gravity. We kind of understand it. Not really. There's a lot of stuff in there we don't. We know what it does. but we don't really necessarily understand it as well as we'd like to. And more importantly, who cares if we go figure it out better? What do we get out of that? Well, I think I can answer those questions. That's coming up on a new series on the channel. So we'll talk to everybody soon. Don't forget to click like and subscribe. We'll see you on the next video.